Good morning. I'm going to show you what I'm looking for in graphs. I've already gotten started here by using a template. They have insert template in your OneNote, so you can put in some graph paper. They also conveniently have in the drawing tools an axes drawer, so you can see that up here. There's an axes drawer, so you can draw that right in. And I've started with labeling my graph. So I named it the number of marbles a spaghetti bridge can support depending on number of spaghetti. So the important thing I'm looking for in a title for a graph is that it has the independent the independent and the dependent variable, number of marbles, dependent variable. So we've got independent and we've got dependent variables in our title. If you had two dependents, like pennies and bolts, you would need to identify both of them. The letters in between should help you recognize which is independent and which is dependent. But otherwise, the main thing I'm looking for is all the variables are listed in that title. The next thing is we almost always are going to put the independent on the x-axis unless there's time. In which case time is always on the x-axis. Time is always going to be on the x-axis. We'll see why later. It lets you compare position, velocity, and acceleration graphs as long as you always put time on the x-axis. So no matter how you do a lab with time, that's where it always goes. But otherwise, you generally put your independent variable on that x-axis. So in this case, that was number of spaghetti. Notice in my titling of the axes, I always put the title as well as the units. So over on our x-axis, we have weight, and then we also have these units with it as well. And the spaghetti one's redundant, but I still wrote both of them to make a point. Okay, next step is we are going to plot or scale our axes. And my pretend data trial had 6 spaghetti and 20 marbles. The key to this is your x-axis will always start at 0, okay? I know you guys want to use the zigzags. We're not going to use the zigzags on the x-axis, and you may not use the zigzags on the y-axis anywhere between your data and the y-intercept because you want to be able to track your best fit line into where it runs into the y-axis. So you can use the zigzags, I guess, but you wouldn't need to because it would be outside your data range. So just stop your axes. So you shouldn't have any zigzag axes in this class. And then on this x-axis, we're going to have 1, 2, 3, 4, 5, 6 spaghetti in my trial. If you had 8, obviously you would include all 8. Over here, we're going to have, let's see, 2, 4, 6, 8, 10, 14, 16, 18, and then actually I think I go up to 20, so I'll need to go up to 20. Notice I use the whole page. I know on OneNote that's a little bit different because you can zoom in and zoom out. If we were doing this on paper, though, I would want you to use the whole page. There is precision in graph paper in the sense that it is a ruler. So if you thought about back in chemistry where you talked about a meter stick that had no centimeter markings and how it's very imprecise, or a ruler that had centimeter markings but no millimeters, that you lose those sig figs, that's also true on graph paper. If you use graph paper and you really spread out your data, you retain your sig figs and your precision in your measurement. But if you squinch them all up and said, I'm going to do 1, 2, 3, 4, 5, 6, only 6 spaghetti to there, then I wouldn't be able to see very much information. And we do want to make sure that we are spreading it out and using it like a ruler so that our best fit line makes a really good average of our data. Okay, so next thing, we're going to mark our data on here. So in my example, at 1, I had 1 spaghetti. I had 1 trial with 2 marbles, 1 trial with 3. At 2, I had 2 trials with 5 marbles. So you can indicate 2 data points are in the same place by making a little bullseye, circling it. That means there was 2 data points there. For 3, I am here at 11 and 9. For 4, I actually got another one at 11, and then I got one at 12. For 5, I got 15 and 17. And then for 6, I got 20 and 19. Let's see if I can eyeball that. It's hard when it's so detailed, right? All right, so there's all my data. I put that on there. In this case, both of these trials are, they're not really separate from each other. You could do them in any order, which means I can use the same color. It doesn't matter which one I did first or second. Some experiments, it will matter which you did first or second because it will rely on previous data in that trial, in which case you would want to do it in different colors to show if one trial is always above the other trial. But this case, the 2 trials, doesn't matter what order, so you can do them in the same color. If you were doing another type like pennies, you would do those in another color so you could see them separate from marbles. But I noticed that all the groups were good about that, so I'm not too worried. All right, our next step is to do our line of best fit. I don't have my ruler, so I'll use my POGIL guidebook. And you just need any sort of straight edge. And I know that Desmos will do this for you. Google Sheets will do this for you. It'll give you a line of best fit. But again, you might need to do this by hand on the AP. So it is worth practicing and knowing how to do it. Also, you'd be surprised at how good human brains are pattern recognition. It turns out we're almost too good at pattern recognition. That leads to a lot of implicit bias and all that. But in terms of graphs, it means that we're almost as good as a computer at finding that line of best fit. Our R values might not be quite as good, but they're pretty good, and you will usually find that your slope that you get is statistically comparable to whatever Desmos or Excel spreadsheets get once you consider sig figs. Like maybe Desmos gets 1.78 and you get 1.73. Same thing, because we know that last digit is an uncertain digit. All right, so I'm going to get a new color so we can see it better. How about blue? I'm going to, sees me touching the screen. So, okay, let's line that up. That looks pretty good. You're kind of looking to have half your data on one side of the line, half on the other. Might have been a little low. It works better if you have a transparent ruler so you can see both, but it's okay. So things you can look for to get data from, or data points from, to do your line of best fit are points that are right on your line that are data points. Those are awesome. Another thing you could look for is intersections in the graph paper. So it is nice to have your data points far apart. So maybe I could even use this one. Well, there's one there. I'm trying to look for an example. Like right here, if none of your data points were on the line, you could use an intersection of your graph paper because, like I said, it's a measuring tool. It is a ruler that helps you measure your line of best fit. So intersections are fine, data points are fine. Since we do seem to have 2 data points on the line, I'll just use those for today. So we know that this one and this one we'll use for our line of best fit. This one is going to be for spaghetti, comma, what was that, 12? Yeah, 12 marbles. Notice I put the units in my coordinates. In physics, the only time you can get away with not using units is a very set number of cases, things that are coefficients, like if you're multiplying your entire equation by 2, or the coefficient of friction. Otherwise, you're going to put units on everything. So 1 spaghetti, comma, 2 marbles. There. And we want to pull off our y-intercept before we go to make our equation. So down here, I see that is negative, well, it's going to be 0 spaghetti, comma, negative 1.5 marbles. And the reason it's important is I know in math class they taught you can use the 2-point method and find your intercept. The problem with that is that then if there's any error in your 2 points and they're twisting the tilt, it's going to really throw off your intercept. So what you do want to do on these graphs is look at where the intercept is and use that value. You can occasionally force it to be 0, but you better have a very good reason to force your intercept to be 0. And if it doesn't look like 0 when you know it should be, you got to be thinking about what happened that you didn't expect, what error is there in there. Okay. So we're going to use 1, 2 and 4, 12. Let's bring that down here for our calculations page. Often in a lab report, this will be on a separate page, but for continuity, I'm going to do it right here. We are going to use our y equals mx plus b format. Now, remember, this is a format or a template, if you will. It is not an answer unless I ask which template are you using. If I ask you what is the equation and you say y equals mx plus b, that is not going to cut it. There's no information in there. That would be like if someone said write a 5-paragraph essay on Hamlet and you said introduction, paragraph 1, paragraph 2, paragraph 3, conclusion. They would say, like, what did you just tell me? That's the format for an essay. That's not an actual essay. So you need to put the information in the equation, not just tell me what the template is. So in this case, our y is going to be number of marbles will be equal to, or you could say weight, actually. Technically, that's weight. Weight in number of marbles equals, we'll come back to m, and then times number of spaghetti plus whatever our intercept is going to be. Now we need to find this m. M, we're always going to use rise over run. So our 2 points are this 4 and 12. So just as a review, although I think everyone here is pretty on top of it, your rise over run is going to tell you that. So it's going to go up by 3, It's going to go up by 10 marbles over 3 spaghetti. All right. Okay. So we are going to have our weight equals that 10 marbles over 3 spaghetti. And also you can do that from y2 minus y1 over x2 minus x1 as well. But I like graphical things. If I'm going to make a video, may as well be graphical. And then we're going to put that intercept in that we read off. So that was 1.5 marbles. Okay. I would not call this correct because this slope has infinite sig figs. And while we're not too picky in AP, you just need 2 or 3 because they aren't grading that on the AP. You can't have infinite. They will grade that. So 10 over 3 is 3.3333333 forever. Not good. So we got to simplify fractions so that we can put in the appropriate sig figs. So our weight is going to be 3.3, and this is in number of marbles. It's going to be 3.3 marbles per spaghetti. Notice I kept the units on my slope, right? And then over here, we're going to have number of spaghetti minus 1.5 marbles. And I would call this a correct answer for what is an equation that represents my data or my graph. So this is the representation of my data. I would call it, some people call it a model of my spaghetti bridge. But we're going to be a little bit more general too. We always want to have a general equation to talk about the general model of the world. In other labs, that will be the equation we get. For instance, velocity is change in position over time, or all the kinematics equations. All those things are equations we can get from graphs. So those are called general equations where you could do it for any position, any velocity, etc. So we need to do that here. So if we're going to write our new general equation, I want to open. There we go. I want another color. Green. Okay, so we're going to have weight and number of marbles is going to be equal. We want to think of what does these units mean. So 3.3 marbles per spaghetti, as we talked about in class, per means for every one. So I can hold 3.3 marbles for every one spaghetti. So that's going to be my average spaghetti strength times number of spaghetti minus, and we said our intercept was the weight of the cup. And then this could be done in any units, whether it's marbles or pennies or anything. One way to always check your work in your equations too is to check that the units work. So up here you see, if they cross out these spaghetti, I get marbles, 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 everything matches, we're good to go. So I checked my work. I came out with my equation for my data. And I also came out with a general equation. And that's the type of thing I will be looking for all year. So I hope you enjoyed that video, and I will see you soon.